All right, so we're warming up. We're trying to simplify now. Log base 8 of the cube root of 64. That's an expression, right? There's no equation. We talked about yesterday converting a log expression into its equivalent exponential form because we think better in terms of exponents. So we can't do that unless it's an equation, though. It has to be a complete sentence, not a sentence fragment. So what could I do to this expression to turn it into an equation so that I can convert that equation to exponential form? I can set it equal to x, right? Very good. That's what they were yesterday when we started. Just say, let it equal x, and now x is the simplified version, right? That's, again, the power of algebra. If you don't know what the answer is, the unknown, call it x. Now we can convert it using the around the world trick, or however you want to do it. 8 to the x power is equal to the cube root of 64. Okay, so now we've taken a step away from solving for x, but we've put it in exponential form, and we can use the GTBTS method if it works, which stands for what? Raven, did you watch the video? You did not. Okay, well, someone tell Raven what GTBTS stands for. Get the bases the same. Get the best. That I like that too. Get the best out of life. Get the bases the same. So if I have base 8 here on the left, question is, can I write the right-hand side as a power of 8? So you start with the number 64. Well, of course, 64 is 8 squared. And then how do we get rid of the cube root and write it as an exponent? It's to the 1/3 power. And you can actually skip that step if you're good enough, because the next step would be to multiply them. And that gives us then 8 to the 2/3. And because exponential functions and log functions are 1-to-1, only because they're 1-to-1, then we can say, so by theorem, x has to equal 2/3. Okay, it's not an algebraic step. If you don't want to have to write the word so, which is a consequence of the theorem, you don't have to, but then you have to do this. Then you have to show me that you're taking log base 8 of both sides. And that's just a lot more writing. Okay, everything has to be clearly communicated. If you do that, then you can go straight to your answer, because now I know what you're doing. But if you're just going straight to the equating the exponents, it's by theorem. All right, now let's see why this also works. The inverse operation of exponentiating base 8 is logging base 8. So if you take log base 8 of both sides, on the right side, what's log base 8 of 8 to the x? It's just x, right? Because you start with x and you exponentiate it base 8, 2 steps to the left, and then you log it base 8, 2 steps to the right, and you're back where you started. Same thing over here. Log base 8 of 8 to the 2/3 is just 2/3. So if you don't want to write the so, you got to do that. I think writing the so is a short price to pay for having to write all that, don't you? The GTBTS method. So x equals 2/3. Now, you might get good enough to realize that you don't have to do all that. You could just say log base 8, 64 is 8 squared to the 1/3, that's 2/3, boom. All right, so let's say you didn't set it equal to x. I showed you 2 ways to algebraically do it, right? Get the bases the same or do the algebra. If you left it as an expression, you might just be able to say, hey, look, it's log base 8. Can I write the argument as a power of 8? Well, yeah, it's 8 squared to the 1/3, that's 8 to the 2/3. And now we can go straight to the answer. What's log base 8 of 8 to the blob? It's just the blob, right? It's just 2/3. Anytime the base and the argument space are the same, they undo each other. They're inverse operations, okay? And that's what we were trying to get to over here yesterday when we were going through these properties, okay? Let's go through these very quickly. Log base 10, that's the common base. You don't need to write it. Log base 10, if you see log, it's implied 10. So log base 10 of 1 is 0, okay? And the reason log base 10 of 1 is 0, it's always good to do this in your head, it's because 10 to the 0 is 1, right? Convert it to exponential in your head. Now, as we said yesterday, what that means then is on the graph of log base 10 of x, whatever it looks like, it has an x-intercept at 1, 0, which makes sense, because if logs and exponents are truly inverses of each other, 10 to the x, the exponential function, has a y-intercept at 0, 1, its inverse function has an x-intercept at 1, 0. Remember in algebra how you found inverses? All you do is you interchange x and y. So if 0, 1 is a point on the exponential graph, flip it around, 1, 0 is the point on the inverse log graph. Now, what's log base 10 of 10 to the first? 1, okay? What's log base 10 of 100? I think we were doing this in the 2, right? Because that's log base 10 of 10 squared. What's log base 10 of 1,000? 3, good. So log base 10 is nice when it is a power of 10, you just count the number of zeros. What would be log base 10 of the square root of 10,000? Or let's do 100,000. That's better. Well, let's see. 100,000 base 10 is 10 to the what? How many zeros do we have? 5. And then the square root's to the 1/2 power, right? So 5 over 2. So this is equal to 2.5. Yeah. See how we can do that? If I can write the base as a power of 10, I've got it. So in general, this is what we're looking at. Log base 10 of 10 to the x is x for any x. All right. And again, if you want to write the 10 there, just so you can see it, log base 10 of 10 to the x is x for any x. X could be a number, x could be x could be an expression. What that does is it locks in the inverse nature of logging base 10 and exponentiating base 10. The order doesn't matter, so we can do it the other way around. What's 10 to the log base 10 of x? It's also x. In other words, you can write it like this. You could say log base 10 of 10 to the x is x, and that's the same as 10 to the log base 10 of x. It doesn't matter if you exponentiate it first and then log it, or log it first and then exponentiate it. They're inverses of each other. If you start with x, you're going to end with x, right? 2 steps tails left and then 2 to the right, back where we started, or 2 to the right and 2 to the left. Is that? I didn't hear what you said. What? Oh, is that a song? 2 steps to the right, 2 steps to the left. Oh, that's part of the Cupid Shuffle. Oh, okay. It's a good song. I don't know the song, but I can follow the directions. Yeah, yeah. 3 claps now, y'all, or something like that, right? Yeah, yeah. Okay, now that's base 10. Remember, the natural base is base E, and we write that as ln. So when you see ln of x, that's really log base E of x. We want to try and think in terms of the natural log. So what's the natural log of 1? It's 0, because log base E of 1 is log base E of e to the 0. Now, what that means is on the graph of the natural log of x, there's an x-intercept at 1, 0. What's the natural log of e? It's 1, because it's really log base e of e to the first. What's the natural log of e cubed? 3. What's the natural log of e to the fourth? 4. What's the natural log of 1 over e? -1, right? Because that's the same as e to the negative first. What's the natural log of the square root of e? That's 1/2. Get it? Because the natural log is log base e. So we can generalize that like this. The natural log of e to the x is just x, because it's log base e of e to the x. So it's really the same property that we did with base 10. It's just with base e. And then, of course, we can compose it the other way. So e to the natural log of x is also x. So if you want to write that in one line, the natural log of e to the x is x, which is the same as e to the natural log of x. When you compose 2 functions back to back in either order, you get where you started, okay? Now we'll generalize the same thing for any legal base. Remember, the legal bases are between 0 and 1 and greater than 1. If it's between 0 and 1, it's decay. If it's greater than 1, it's growth. So for any base legal, what is log base b of 1? It's always 0, because b to the 0 for any numbers in that interval is always 1, right? Any number to the 0 power except 0 is 1. So that means on the graph of log base b of x, whether it's logarithmic growth or decay, we'll look at those graphs later, there's an x-intercept at 1, 0. all graphs of that form, whether they're growth or decay, pass through the point 1, 0, just like anything of the form b to the x passed through the point 0, 1, whether it was growth or decay. What's log base b of b for any base? It's 1. Okay. And now we can summarize this. Log base b of b to the x is x. That's exponentiate it and then log it, or do it the other way around. Log it and then exponentiate it. So we can write those like this. Log base b of b to the x is x. Or you could say b to the log base b of x. When you compose two functions back to back, what do they do to each other? Undo each other. Yeah, you're right back where you started. And again, this x is a placeholder. It could be a number. It could be an x. It could be a pink elephant. It could be an expression like x squared plus 4. It doesn't have to be plain old x. Okay. All right. Let's try out example 2. Evaluate. Log base 7 of 7 to the 3x squared plus 2. What do you think? 3x squared plus 2, right? That's this exact same thing that we just did. That's this one right here. Log base b of b to the blob is just the blob. Log base 7 of 7 to the blob is just the blob. Yeah. What's the natural log of e to the x? Remember, the natural log is the same as log base e. So the natural log of e to the x is really log base e of e to the x. It's just x, right? Again, you want to start thinking, though, in terms of natural log. If you go on to take any higher level math, you're going to have to think in terms of natural log. What is 5 to the log base 5 of 5x? 5x, yeah. Let's write it the other way. What is log base 5 of 5 to the 5x power? It's also 5x. See, it doesn't matter the order in which we compose it. What about d? What's e to the natural log of x? Well, x, right? Because that's the same as e to the log base e of x. That's just x. And then finally, e, what's log base 22 of 22 to the x? It's just x. Let's write it the other way. What's 22 to the log base 22 of x? Just x. Those questions are not designed to be hard. All those questions are, they're reinforcing this property. This property down here is probably the most important one. And then this property right here, the fact that the log of 1 for any base is 0, that's the second most important. It follows directly from here, because remember, 1 is the same as b to the 0. But those are the two that are the most important. Let's do example 3, which will kind of reinforce the other properties. Evaluate them. What's log base 5 of 1? It's not 1. 5 to what power is 1? 0. Let's set it equal to 0 instead of write 0 below. When you have a number like this and you're evaluating, it's good to reinforce it. Log base 5 of 1 is 0 because 5 to the 0 power is 1. Remember, the graph of log base 5 of x passes through the point 1 comma 0. What's log base 1/2 of 1? 0. That's going to end up being logarithm decay, but it doesn't matter. 1/2 to the 0 power is still 1. So log base 1/2 of 1 is 0. What's log base b of 1? 0. Because b to the 0 for any legal base is 1. Yeah. This is repetition here. What's log base 12 of 12? 1, because that's the same as log base 12 of 12 to the first. That's 1. So look, if you confirm this by doing around the world, log base 12 of 12 is 1 because 12 to the first is 12 to the first. Yeah. What's log base b of b? 1, because b to the first is b. What's the natural log of e? 1. Yeah, again, in the meantime, until you're used to the natural log, if you need to write it as log base e, that's fine. So we really, when we say the natural log of e, we're talking about log base e of e to the first, which is 1. So what's the natural log of e? 1. What's the natural log of 1? 0. What's log base 10 of 1? 0. What's log base 12 of 1? 0. What's log base, give me a number, 27 of 1? 0. What's log base 1 over 400 of 1? 0. Yeah. What's the natural log of 1? 0. Good. What's the natural log of e? 1. What's log of 10? 1. What's log base 7 of 7? 1. What's log base 2/3 of 2/3? 1. Good. Oh, look, there we go. What's log of 10? It's 1, because really it's log base 10 of 10 to the first. Yeah. All right. So here's the summary. We're summarizing, we're practicing, then we're summarizing again, then we're practicing, and we're summarizing some more. Super important. This property right here that we already wrote down is called the conversion formula. That allows you to go back and forth between the two different sentences. They have to be equations, right? That's the if and only if statement. You can do the around the world if you're going from left to right, but if you're going from right to left, you know, you can either log base b both sides, like we talked about yesterday, algebraically, or you can just know where the parts go, right? B is the base, the log is y, so y is the exponent. That becomes your argument, right? Okay. And then this is one of the first most important one, log base b of 1. That means that there's an x-intercept at the point 1, 0. Log base b of b is 1. That's okay. But then the most important one is this right here. That reflects the inverse nature of exponential and log same base. You can compose them in any order. It doesn't matter. All right. Conversion. All right, so we kind of know what logs are. We've been practicing. What we're going to do now is we're going to deviate from the notes for just a second. And I want to give you all a little opportunity to do some what we used to call drill and kill, but it's just practice on your own. So let me walk you through it. If you go to your Canvas course, right, you click on the goofy guy. Look what I put as my background for Calculus Maximus. It's me dressed like a gladiator. And look what I put for the background for the academic Precal. It's me dressed like a nerd. Y'all actually got the coolest background picture. I'm throwing you the peace sign. Go to modules and go to the bottom. We discovered this website, Delta Math, during the pandemic because it's all 9, and we can assign problems. And then y'all can work them independently, and you can work them at your own pace, and they give you feedback if you get them wrong. So it's good for us now when we're practicing this type of stuff to go over it together. Go to Delta Math join codes. All right. It says on your iPad, follow the link to join your class. You'll need to create a free account once you get in there. You can just say you can join with Google. It's free. So click on your second period Delta Math and join. Okay. Now, while you're doing that, I want to go over what some of these problems that I'm having you do. Okay. If you have something of log base b of y equals x, there are 3 locations in there, right? 3 different locations. We like to solve these by converting them to exponential. So far, the ones that we've looked at, we've known the b and the y. We've known the 2 things on the left, okay? But as long as you know any 2 of those 3, you can always find the 3rd, right? So let me give you an example here. We've already seen the ones where we don't know x. If I don't know what b is, let's see what this looks like. This could be log base x of 36 equals 2, okay? I might ask you to solve for x. Well, x is the base now, right? The unknown is the base. The legal bases, remember, are between 0 and 1 or greater than 1. Can we have a negative base? No. How would you solve for x here? If it's in log form and you're kind of squeamish still about log form, convert it to exponential form. Let's see what that would look like. X to the second power equals 36, right? Now I've turned it into a polynomial equation, a quadratic. But at this point, it could still be a cubic or a quartic or a fifth degree. How do I undo squaring both sides? I take the square root. If it were x cubed, I would take the cube root of both sides. I think the delta math goes up to x to the fifth. I would take the fifth root of both sides. Now, remember, when I do that, I want to consider plus or minus. So I get x equals -6 or x equals 6. I always consider plus or minus. But now, in the context of what I'm looking for, do both of these work? I'm trying to find the base of a log. Can the base be negative? No. So the answer is just x equals 6. So on the delta math assignment, you'll just go into the box and you'll hit 6. You don't even have to put x equals. You'll hit 6 and you hit enter. Okay. So that's the second variety. You have an unknown base. Okay. The third variety is actually the easiest. If you don't know what y is, you're trying to find y. Here's an example. Log base 4 of x to the fourth power. Okay. So now, for the first time, we see a log equation, but it's the argument that's unknown. Well, once again, how are you going to solve a log equation? If you're squeamish about it, convert it to exponential. So 4 to the fourth power equals x. Well, that's easy now. All we got to do is evaluate that. 4 to the fourth power, that's not going to be fun. That's 4 squared times 4 squared. That's 16 times 16. You might have to go out to the side and do some old school stack division. Okay, so that's 36, carry the 3, that gives you 9, put a 0, you got a 6 and a 1. That's going to be 6, 256. I never memorized my powers of 16s, but I can certainly do stack multiplication. So there's the answer. So on delta math, you would type in 256. Okay. So now we know that it doesn't matter where the variable is. It could be the argument, it could be the base, or it could be the log itself. If you use the around the world trick and you convert it to exponential, you can either get the bases the same, you can either solve the polynomial equation by taking the nth root of both sides, and sometimes you might have to find that number. You might be asked to find like the fifth root of a big number, but trust that the answer will be either 1, 2, 3, 4, or 5. So you just try it out. What's 5 to the fifth? Go try it out. Or it might be the easy one where you don't know the argument, and when you convert it to exponential, you just evaluate your answer. Okay. So here's what I want you to do. I want to give you about 10 minutes to do 20 problems. It shouldn't take you that long. If you go now to your Canvas course and go to the Delta Math Intro to Logs, that's your assignment. And now you should be able to click on that link and it'll give you, well, yeah, I'm going to log in with Google. Anyway, it'll give you, let me see what it looks like. Well, I'm not going to show you here. What it's going to do is it's going to give you, when you go there, it's going to give you this screen, and you're going to have these rows right there. And it's going to say like 0 out of 1 or something like that. I'm not sure. But there's 20 of these little rows. All you got to do is click right here. There's my hand. Okay, it's a red hand. Just click right there and it'll take you to your first problem. And then all you got to do is type in your answer, submit, and it should take you to the next problem. Okay. But you have to join first, right? Of course. Does anyone see it? Oh, okay. Oh, crap. Okay. Okay. Pause. Okay, so it is fixed. You should be able to go straight to Canvas, go to the Intro to Logs assignment, click on the one link, and then it'll take you to there. You can join with Google if you want. You don't have to create an account. And then just click on the first row and it'll take you to all the rest of them. All right, so I'll give you 10 minutes to do that. Submit it when you're done. I think when you finish the last one, it automatically submits it. I'll get to see your results on the other end as well. 10 minutes to see. Okay, so anything that I ask you to evaluate, like a log expression without a calculator, is going to be a relatively nice number. You're going to be able to evaluate it. But sometimes I'll give you something like this. What's log of 21? Well, first of all, what's the implied base? 10. So if you want, you can do those two little tricks there. You can put the base so you can see it, and you can set it equal to x so that you can convert it. So now we get 10 to the x equals 21. So 10 to what power is 21? Well, golly, 10 to the first is 10. That's too small. But 10 to the second is 100. That's already way too big. So I don't know much about the solution other than it's going to be 1 point something, right? And it's going to be some number that's probably closer to 1 than it is to 2, because 21 is closer to 10 than it is to 100. Well, luckily your calculator is programmed to do base 10 and base E. So make sure you know how to access this one on your iPad, right? You go to Corpus World, you go to other maths, the second asterisk downloads the ROM, the first asterisk takes you to this website, select the conditions. Just a reminder, if you're loading it, once you select the terms, you got to click this ROM button, and then it'll ask you to upload the file, and you just load it. It says TI-84 SE Silver Edition, okay? And then when you're using it, remember it times out, so you want to hit the pause button at the top. Well, I'm about to access mine, so I'm going to hit play. And then all you got to do is type in the log button, which is right there to the left of 7, type in 21 and hit enter. Boom, and there it is. I know that it's actually x equals 1.322. Okay, very nice. And watch, you can verify it. Now you could say 10 caret, and you can hit second negative. Remember, second negative recalls the answer. If it's the right answer and I hit enter, I should get what? 21. Boom. It's nice. Okay. Same thing over here. Let's look at the natural log of 12. I'm going to say that this is log base E of 12, and I'm going to set it equal to x. Why? So that I can convert it, right? So e to the x equals 12. Now remember, e is 2.718. For practical purposes, when you're trying to come up with an approximation here, you can think of e as like 3-ish. What was that? Yeah. Oh, it vibrated. 3-ish. So 3 to the first is 3. It's too small. 3 squared is 9. It's still too small. 3 cubed is 27. Now that's too big. So I know that x has to be approximately 2 point something. Well, once again, if it's a natural log, that's base E, your calculator knows what that is. So now to the left of the 4, ln of 12, hit enter, and there you get the 3 decimal approximation. X is equal to 2.484 or 485. And with the correct answer still there, you could just try it out. E, second ln to the second negative, you get 12, okay? So if it's not a perfect factor, I'm sorry, if it's not a perfect power of the base, you can evaluate it on the calculator as long as it's base 10 or base E. Your calculator actually uses what's called a Taylor polynomial to evaluate that. It uses plug and chug on some high-powered polynomial, which is a pretty interesting concept. It's a BC topic. See you later. Bye-bye. So tomorrow what we're going to do is, what do we do if it's a base that's not 10 or E, like base 7, and it's not a perfect power of that base? How can we use the calculator to get it to us? Okay. Perfect ending.